Alright, so today we're going to talk a little bit about optimization. I had some questions from students about this, so I used Khan Academy here. I just called up their optimization question. I thought we could work through it. What's the maximum vertical distance between y equals x plus 2 and the parabola y equals x squared, and it has a domain from -1 to 2. So I'm going to just do a quick and little hand graph to this. My computer is just a hair slow, but I think we say that we have x plus 2, we know that that's going to be that line, and it's going to be a solid dot on this end. Woo. We're going to live with that. Alright, and the parabola g equals x squared, we're pretty used to this, the mother function. And they picked this because it hits on the endpoints, right? It hits at 2, 4, and 1, 1. And it's asking for the vertical distance, the tallest vertical distance this way. I'm going to call that h of x. Alright, and h of x is going to be equal to the top function, which is f of x, minus g of x. Alright, now you can tell this is my first time doing this, that's for sure. I want to maximize this distance in here. Well, if I want to maximize the distance, I have to have it all in terms of one variable. I'm not going to do a derivative with respect to time, I'm going to do it with respect to a variable. Well, because these functions are already like that, this problem is actually fairly simple to optimize, because when you do it, this is the height between the two curves at any value of x. So if I set the derivative, find h prime, so that I can optimize for a max or min, I get the derivative of x is 1, derivative of 2 is 0, minus 2x. Alright, that looks great, and I know I want to set it equal to 0. Well, this is one of those functions where I think we can all see that this equals 0 when x is equal to a half. Alright, so it's saying at a half is the major distance. Now, if I think about this and kind of get a feel for this, I think that's probably right, because at a half here, you can tell it's pretty darn tall compared to everywhere else. So now we have to check when we do an optimization. This is also an extreme value. This actually is going to be the maximum distance, we can tell from the graph. So the question was, what is the maximum vertical distance between the line and the parabola, not where does it happen. So I have to take my half back into this function. So go back to h of a half, and I get what? Half plus 2, which is 2.5, minus a half squared, which is a quarter. So 2.5 minus a quarter is 2.25. So I would say the height of this thing is at a half is 2.25, and that is the maximum height. Now I can tell by the endpoints here and here that the distance at those points is 0. So the extreme value theorem says we should check the endpoints for maxes and mins too on a function. And h of x this time could have those things happen since it is a function. But in this place, I'm going to go 2.25 for Khan Academy. It should accept that. And there we go. So we're going to record that next one here too. So we're going to go to a new page. It says consider the function f of x equals 9 minus x squared. F of x is greater than the output is greater than or equals 0 only. The shaded region is a isosceles triangle formed by the join the point 0, 0 and x comma f of x, which means if this is isosceles, and since this has the axis of symmetry here, that this point is negative x comma f of x. It's going to be an even function across. What is the largest area of the triangle that satisfies the status condition? So you want to optimize this area, okay? We want to optimize the triangle area. So the first thing I think of is, okay, I'm going to have a triangle. And I know that if I want to optimize the area of a triangle, to start with, guys, is simply 1/2 base times height. That's where I'm going to start with this problem at. Alright, well, the base here is 2x. It's negative x one way, x the other, so the length is 2x. The vertical height of this function right here, this time, is simply the output of f of x. Now if you look at the graph on the left, on the Khan Academy site, you can see that that has to be the height. So immediately I get the triangle area, which I'll just call A from here out, is 1/2 times 2x times f of x. Now a lot of times we could call that y, and again you can't do differential or implicit differentiation with this. You have to get to one variable. So I'm going to get this to, the area is x times, well, the f of x is simply the y value, 9 minus x squared. And again, in these cases it almost always makes sense to distribute. So I get 9x minus x cubed. Well, that's going to be the area of the triangle for any value of x. And we want to maximize, so we're going to optimize this equation. We're going to take the derivative, a prime is simply 9 minus 2x squared, or not 2x squared, sorry, 3x squared, let's say that correctly. And you take the derivative with the power rule, we know that comes down. So this is a 3. Now we're going to set a prime equal to 0. And again, this is one of those times I think we can tell by where it happens. That happens at x. We move the 3x over, divide by 3, get x squared equals 3. So it happens at plus and minus square root of 3. Alright, now again, we would expect that to be the maximization of this triangle. Alright, now if I want to check, I can check using the first derivative. What happens when what happens to a prime of x when x is less than square root of 3 but greater than 0? Alright, and if you plug that into the derivative here, you're going to see that this is greater than 0. And if I go a prime x is from square root of 3 to 3, because we can't go there, we don't want to have a triangle of area height 0, and I say 2, I put in 2 here, I find that I get that that's 12, it becomes negative. So look here, the first derivative rule here says it goes from positive to negative. Well, that's obviously a local max. So we know that's the maximum. Again, it doesn't ask for where it happens, it asks what's the largest area. So I go back to my area triangle equation way back up here, and I'm going to get this, when I plug square root of 3 in there, I'm going to get 9 square roots of 3, and I'm going to take square root of 3 cubed and get 3 square roots of 3. So I think the answer is 6 square roots of 3. Alright, divided by, nope, it should be 6 square roots of 3. So we'll see if it's none of these. I obviously got a math mistake up here. Where did I make it? And it's the hint, and there's the first hint. Let a of x denote the area. There it is. So they have the same area of x equation. I think I made a math mistake someplace. Between 0 and 3. They set the regular, they find square root of 3. Did I make a math mistake plugging it in? So they find the area is 0, they find 3 roots of 3. And then they did a of 3. I think this is one of those times I have to disagree. Unless they're going to allow the triangle to be flipped the other way, they cannot. And this would be 6 square roots of 3 here, 2 anyway right here, we all agree. You think about a of 3 here, I don't agree with this because 3 times 3 is 9, 9 minus 27, well that's 0. So the maximum area, they did a math mistake right here. It is 6 square roots of 3. So we're going to report a mistake here. 9 square root of 3 minus 3 square root 3 is 6 square root 3, which is answer. Well, I've never done this, so I'll submit this. Oh. And there we go. So we'll submit that. And there's my mistake thing. But I guarantee, I'll tell you guys from our work here that the answer here is 6 square root of 3. Again, 2 optimization problems. Alright. And keep practicing.